Hello and welcome to lesson 6 on vertical dynamics. So in this video we are going to start looking at how forces apply when objects move up and down vertically. Okay, so the title kind of says it all here. So objects that move upwards or downwards often have two main forces acting on them. So we have the downward force of gravity. That's always going to be there. There's no way to get rid of that. Okay, it doesn't mean that you're going to be accelerating downwards all the time. Like chances are right now you're sitting in a chair watching this video and you're not accelerating at all. And that just means that there's another vertical force that's present. Okay, so there's also an upward applied force. So if you're sitting flat on something, it's going to be a normal force. It also might be like tension in a cable. Say you were like hanging from a cable or you're like hanging something. It doesn't have to be a person, but we'll see kind of this in action here in a little bit. Okay, before we get going though, there's a couple questions I want you just to think about. So feel free to pause the video right now, read these 3 questions, see what you can come up with, and then hit play. So without any additional forces beyond gravity, what's the greatest acceleration an object can have in the downward direction? We're going to assume all this to be happening on Earth. So it is negative 9.81 meters per second squared. Okay, now things can accelerate downwards at a greater rate than that. So for example, if you were holding on to something in your hand and you take your hand and you move it downwards really, really fast, you can give it an acceleration greater than negative 9.81 meters per second squared. Like you could move something from point A to point B faster than if you had just dropped it. Okay, so you can get a greater acceleration, but you're going to have to put some force into that. Okay, and this question says without any additional forces beyond gravity. So if you just let gravity do its thing, negative 9.81 meters per second squared, think back to the video on the bowling ball and the feather, everything accelerates to the center of the Earth at the exact same rate, and that is our gravitational constant. Number 2, if an object accelerates downwards with an acceleration less than negative 9.81, how does the applied force compare to the force of gravity? Well, if it's accelerating downwards less than 9.81, it means that my free body diagram would look like this. Okay, where I'd have a smaller upwards force than my downward force. Okay, so there's a couple things here. How does the applied force compare to the force of gravity in terms of direction? It's in the opposite direction. Okay, now sometimes people go, well, how do you know that? Like, just from reading the question. Well, if it was in the same direction as gravity, okay, so if it looked like this, my acceleration would be greater than 9.81 meters per second squared because I have that force from gravity plus the other force and they're acting in the same direction. So if the acceleration is less than negative 9.81, I know that this force has to be opposing it and canceling some of it out in a sense. Okay, so how does the applied force compare to the force of gravity? Okay, so it has to be opposite direction, and then my applied force, my force applied, must be less than my force of gravity. And how do I know that? Well, if my free body diagram looked like this, where my applied force was larger than my force of gravity, this thing would accelerate upwards. Okay, but the question tells us that it accelerates downwards. So the downwards force is still larger. Just the applied force is canceling some of it out. Okay, so this free body diagram over here would be my correct one. If an object accelerates upwards with a positive acceleration, how does the applied force compare to the force of gravity? Well, again, we see that it would be opposite direction. Okay, and this time the force applied must be greater than the force of gravity. Okay, so if it's going to have at least as much force of gravity to cancel that out and then some extra to result in this thing accelerating in the upwards direction. So this, my free body diagram for this one, would look as such, where my upwards force is larger than my downwards one. So to calculate the net force in either of these scenarios, we can use one of these kind of 2 F net statements. Okay, so F net's either equal to the applied force subtract force of gravity if it's accelerating upwards, or if it's accelerating downwards, then it's going to be force of gravity subtract force applied. So it's always whichever force is determining the direction. So if it's going upwards, that means the force of applied is the larger of the two forces. And then I'm just going to subtract away whatever gravity's canceling out. And if it's accelerating downwards, then I have the exact opposite. So force of gravity, and I'm going to subtract away whatever the applied force is canceling out. Okay. If the object is moving at a constant velocity, that means that my acceleration is equal to 0. And remember that the F net is equal to mass times acceleration. So if this is equal to 0, then F net also equals 0. And for the net force to equal 0, any relevant forces must be equal and opposite to each other. So the amount of applied force is going to equal the amount of gravitational force. All right, draw a free body diagram for the following. Underneath, write the F net statement. So in the first one, I have a stationary elevator. Okay, so I have a force of gravity acting on this elevator, and if it's stationary, that means there must be some upward applied force. Okay, now I'm actually going to switch that up, and I'm going to call it the force of tension, since the elevator is likely hanging from a cable of some sort. So in this one, just give me a second to see where my stuff just went here. All right, not sure where it went, but we'll just restart this section over here. So we have a stationary elevator. Okay, Fg, Ft, my F net is equal to 0 newtons. Okay, or I could say like F net equals, in this case, it doesn't matter which one goes first. Fg, and then if you think about, if we did some math here, Ft minus Fg, I want to know how those forces relate to each other. I can add Fg to the other side, and I can see Fg equals Ft. So they're going to be equal and opposite to each other. Okay. B, an elevator accelerates upwards from rest. Okay, so my force of tension should be larger in this scenario. Okay, so Ft is going to be greater than Fg since it's accelerating upwards. So I can say that F net is equal to the force of tension subtract the force of gravity. Okay. For C, a rocket travels upwards at a constant velocity. This is going to be identical to A. Okay, so even though it's traveling upwards, it's at a constant velocity. So it's going to have the exact same free body diagram as a stationary elevator, because in both A and C, my acceleration equals 0 meters per second squared, and it follows that same explanation we just talked about up here. Okay. And a ball falling to the ground with no air resistance is going to just have a force of gravity. So it's just going to be F net is equal to the only force that's present, so the force of gravity. All right, 915 kilogram elevator accelerates upwards at 1.3 meters per second squared. What's the tension in the cable? So I know that it's accelerating upwards, so my force of tension must be larger than my force of gravity. So my F net statement is equal to the larger force, subtract anything opposing it. So MA, I don't have a formula for force of tension on my sheet. Okay, it's also what we're looking for, so there's no point in trying to break that down. And mg. Okay, so what I'm going to do is I'm going to add mg to the other side. And I have ma plus mg. It's equal to the force of tension. I can factor my mass out. Okay, so it's going to become mass onto A plus G equals Ft. Okay, so just kind of finishing this out over here. I have the mass, 915 kilograms. Now, just to kind of state this, you wouldn't have to factor the mass out. You could put it in here and put it in here. That would be fine. Doesn't really change anything at all. So 9.81 meters per second squared plus 1.30 meters per second squared. Give me a second to grab a calculator here. All right, force of tension equals 11,668.995 newtons. And looks like we get 3 significant digits, so we're going to need some scientific notation here. So I'm allowed 1, 2, 3, and I'm rounding here, so 1.17 times 10 to the power of 4 newtons is my final answer. And that would be in the upwards direction. Okay. So we previously talked about how the weight of an object is related to the force of gravity on the object, and that describes the true weight. Okay, so if I asked you like what your true weight is, that's how much you weigh when you're standing still. Okay, now the apparent weight of an object changes when that object accelerates in the upward or downward direction. So if you were sitting on a scale, so imagine like you were on a roller coaster, and you put a scale underneath you and you were sitting on it, and you could see the numbers kind of like in between your legs as you were riding the roller coaster. You would see that the number on the scale actually changes. Okay, now remember, there's a difference between mass and weight. Okay, weight is a force, and mass is a measure of matter. Okay, so obviously as you're going on that roller coaster, the amount of matter your body's made up of isn't changing. Okay, so say you were like 85 kilograms on the roller coaster, you're 85 kilograms all the time. Okay, now 85 kilograms is equivalent to 833.85 newtons. Okay, so you're on the roller coaster and you're sitting still at the beginning. You look down and the scale reads out newtons, and it tells you that you're 833.85 newtons. Okay, now we're going to do a little bit of a visual thing here. Okay, maybe I'm going to switch off the roller coaster for a second, and we're going to talk about like one of those drop rides. Okay, so we have a really tall drop ride, and let's say that like the car that you're sitting in is up here at the top. Okay, so this is you. Okay, and you're sitting on the scale. Now imagine that this thing starts to drop downwards. Okay, and it's racing down towards the ground. Do you think that scale that you're sitting on, as that chair is starting to fall out from under you, do you think it's going to read a higher number or a lower number? Okay, and if you've ever been on one of these rides, just think like, does it feel like you're being pushed into the seat, or does it feel like you're being lifted off the seat and maybe like the shoulder straps are stopping you? And if you've been on one of these before, you would know that as the bottom starts to fall out, it's like you almost like feel like you're lifting up a little bit, and you would be reading less weight. Okay, so when things accelerate downwards, the apparent weight of the person, and we say apparent because obviously like your true weight represents like the force of gravity on your matter. Okay, so that's like your true weight, but your apparent weight is your weight in different situations. So when something accelerates downwards, the apparent weight is going to be less than the true weight, okay, because it's like that scale is almost like falling out from underneath you. Okay, on the flip side, imagine you're sitting down here at the bottom. Okay, let me change colors here actually, just so we can kind of differentiate between these two. So you're sitting down here in the car at the bottom. Okay, that's you. And this time it's going upwards. Okay, so this time, as it's accelerating upwards, are you being pushed into like the shoulder straps holding you in, or do you feel like you'd be kind of like pushed into the bottom of the seat? Okay, and imagine like right now, if I just walked up to the chair you were sitting on, and imagine it was hooked to like a chain, and I stood on the desk and I lifted really hard on the chain. Do you think that would push on the scale harder or with less force? And the answer is that it would push down with a greater force. So when things accelerate upwards, they're going to have more weight. Okay, now the reason I'm trying to get you to visualize this is lots of times people get lost in the formulas and they just like want the formula to do all the work. But by the end of this course, there's too many things to just like memorize formulas for. Like you might have been able to do it in kinematics, but by the time we get to the end of dynamics and we start going into circular motion and work and energy and like, you know, all of these other topics, eventually there's just too much to memorize for most people. Okay, so I really want you to kind of visualize this and imagine sitting on a scale and somebody like pulling the chair out from underneath you. What would happen to the scale? Well, it would read less. Or if somebody like lifted up on the chair, well, it's going to read more. If you can remember that, you'll be able to piece these formulas together, or at least like make sure you come up with the correct answer. Okay, so we got a couple conditions to look at. If the object's at rest, the true weight and the apparent weight are the exact same. The scale's not moving, you're not moving. It's like when you stand on the scale, you know, maybe before you hop in the shower or something like that. Those two are going to be equal to each other. If the object is moving upwards or downwards at a constant velocity, again, the true weight equals the apparent weight. Okay, so the true weight equals the apparent weight. Now, if the object is accelerating upwards or if the object is accelerating downwards, those two no longer equal each other. Okay, now this does not say, so not say moving upwards. Okay, and this one does not say moving downwards. It says accelerating upwards and accelerating downwards. Now I'm going to talk about why that's kind of significant. Okay, so imagine in this scenario up here that we drew, okay, you started from rest and you start to speed up on your way up. In this case, you have a positive velocity and a positive acceleration. So the acceleration's in the upwards direction. In the blue one, you started at rest and you accelerated downwards. So you had a negative velocity and your acceleration was in the downwards direction. So that's fine. Okay, but let's talk about now something like an elevator. Okay, so say this elevator is at the 3rd floor and it's trying to get down to the 1st floor. Okay, so at the beginning, the people are standing on it. Again, some very rough drawn stick figures. Okay, and they've just stepped in the elevator. It's at rest. When this elevator starts taking off, okay, the acceleration is downwards. Whew, that's a little messy. Hopefully you were listening. So it's downwards, and the velocity is downwards. Wow, that's 0 for 2 in, legible writing. Anyways, as this thing continues to drop, down, 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 in order for it to stop right at ground level, what has to happen to the acceleration? Okay, so say it's moving down at like 2 meters per second, 2 meters per second, 2 meters per second, and then all of a sudden at this point right here, it starts slowing down. So it's like -1 meter per second and 0 meters per second. Well, in this section right here, what direction was the acceleration in? The acceleration was opposite of the velocity. The velocity was negative or down, and the acceleration was upwards or positive. Okay, so even though the elevator is moving down to stop at the end, it needs to have a positive acceleration. And the same thing happens when this elevator goes up, except opposite, as if it's going like 2 meters per second, 2 meters per second, and then all of a sudden 1 meter per second and 0 meter per second. In this section here, we see a negative acceleration. Okay, so even though it's moving upwards, as it comes to a stop, it has a negative acceleration. So with elevator questions, you really, really, really have to be careful. Okay, it's not about what direction the elevator is moving in. It's what direction is the elevator accelerating in. So if it's at the top floor and it's working its way downwards, like it's just taking off, then it is accelerating in the downwards direction. It's speeding up in the downwards direction. If it's moving downwards and it comes to a stop, to do that, it has to accelerate in the upwards direction. So again, remember that accelerating upwards does not mean that you are moving upwards. Okay, we talked about this back in like the kinematics section and earlier in the dynamics section. You cannot determine the direction of movement just off of the sign of the acceleration. Okay, you need to know the velocity to be able to compare. Are they both positive? Then it's speeding up. Are they both negative? It's slowing down, and so on. Okay, so you can have an upwards acceleration without ever traveling upwards. And you can have a downwards acceleration without ever traveling downwards. Okay, so those questions lots of times students get wrong because they're like, oh, it'll talk about an elevator at the bottom moving downwards and coming to rest, and they're like, oh, it's moving downwards, I'm going to use the downwards logic, and that is incorrect. Okay, so just to kind of finish this off, if something's accelerating upwards, its apparent weight is greater than its true weight. So the scale will read more than it would have when they were standing still. And we have the opposite when something's accelerating downwards. Okay, so really just try and keep that visual in mind and remember that you're looking for the acceleration, not the velocity. All right, 60 kilogram student standing inside an elevator on a scale reads out the weight in newtons. What number will the scale read for each of the following scenarios? So if it's stationary, the weight's just going to be the regular force of gravity. So this is like our true weight. Stationary, true weight. Okay, so we have 60 kilograms and 9.81 meters per second squared. So 60, 9.81 gives me 588.6 newtons, so 589 newtons. Okay, if the elevator accelerates downwards, okay, at a rate of negative 1.20 meters per second, this should say squared, so we got to add a little 2 in there. Okay, at a rate of negative 1.20 meters per second squared. Now remember, if it's downwards, the true weight will be greater than the apparent weight, or the apparent weight will be less. Okay, so when I set this up, it's going to be that my weight apparent, okay, is equal to the true weight subtract the F net. Okay, so whatever the true weight is, I need to subtract away whatever force is there as a result of the acceleration. Okay, so my true weight is 588.6 newtons, subtract the mass times the acceleration, so 60 kilograms, and my net is 1.20 meters per second squared. Remember, in dynamics, we're already putting negatives in a sense, by saying that we're subtracting. Okay, so if you kind of look and say this force, subtract this force, you've already taken care of the negative. Don't put it in again, or you've kind of doubled up. Okay, so you could say like true weight plus F net, and then put this 1.20 in to be negative, and that would be fine. But the way we're looking at it, I've just had better luck with students along the way, just saying like, these two forces are opposite, this one's bigger, so it's this one subtract that one. So don't put any accelerations in as negative. We're taking care of that already when we choose to subtract. Okay, so if I punch this into my calculator, okay, I get an apparent weight of 516.6 newtons. Okay, so 517 newtons. Okay, now if I am accelerating upwards at a rate of 2.40, this time my apparent weight is just going to be whatever my true weight is, plus the result of that net force. Okay, so my true weight was 588.6 newtons plus 60 kilograms, and the acceleration is 2.40 meters per second squared. Okay. So punching that into my calculator, I get 732.6 newtons, so 733 newtons. Okay, so if you take a look here, if we just kind of recap, in both scenarios, we started with the true weight, and then we related the F net to it. In the event of it accelerating downwards, we take away that net force. In the event of it accelerating upwards, we add the net force. Okay, now I'm going to show you a little bit of a shortcut here, and it's not really a massive shortcut, but it'll save you doing it in 2 steps, or you can do it in 1 if it wouldn't have asked you for part A. So remember that the question could have went straight to part B, and I wouldn't have had this number. I would have had to do all this and then come to part B. So if we look at what it is, it's weight apparent is equal to the true weight minus F net. Okay. The true weight we find using mg, and F net is ma. So we can see where we're doubling up in the masses again. So apparent weight is going to be mass, and then gravity minus the acceleration. Okay, so you could just throw these three numbers in, and you could get to this 517 answer. On the flip side over here, okay, we have the true weight plus the F net. So we have mg plus ma. So factor the m out, g plus a. Okay, so to find the apparent weight, it's just the gravity either plus the acceleration or subtract the acceleration, and then multiply by the mass. Okay. All right, so this brings us to the practice questions. Again, these are intended to be done by you. So please take a look at the questions, try them first, and then just watch the video if you need help with them. Okay, so question number 1, elevator with a weight of 110 kilograms. It's carrying 2 people with masses of 40 kilograms and 50 kilograms. So in total, I have 200 kilograms of mass. Calculate the tension in the cable if it's at rest. So in part A, if it's at rest, the force of gravity is acting on this elevator, and then it's at rest, so I have an Ft. Okay, now I know that my force of tension must be equal to my force of gravity, or else this thing would be accelerating or moving. Well, I shouldn't say moving. If the two weren't equal, it would be accelerating. Okay, but since it's not, they have to be equal. So 200 kilograms times 9.81 meters per second squared gives me 1,962 newtons. Okay, we're looking at 2 significant digits across the board here, so it's going to round up to 2.0 times 10 to the power 3 newtons. All right, in B, if it's moving upwards with an acceleration of 5.0 meters per second squared. Okay, so we're going to just say that this acceleration it's in the upwards direction too. So this kind of goes against what I said earlier. And this question actually should be written a little bit better. But we're going to say that it's moving upwards and accelerating upwards as well. Okay, so what's the tension in the cable? So in this situation, it would look more like this. Ft, Fg. So F net is equal to Ft minus Fg. Therefore, the force of tension is equal to F net plus Fg. So this is Ma plus Mg. So A plus G. 200 kilograms. Oh, wrong way. 9.81 meters per second squared plus 5 meters per second squared. And that whole thing is going to give me 2,962 newtons, which will round off to be 3.0 times 10 to the power 3 newtons. Okay, and then in this one, it's moving downwards with a downward acceleration of 5.0 meters per second squared. So in this one, my force of gravity is my larger of the two. So it's going to be F net equals Fg minus Ft. Okay, doing some rearranging. That's going to tell me that Ft, I would add it to the other side and then subtract F net. It's equal to Fg minus F net. So Mg minus Ma, factoring the M out again. 200 kilograms, 9.81 meters per second squared, and minus 5 meters per second squared. So I have 4.81 times 200, and I end up with 962 newtons, so 9.6 times 10 to the power 2 newtons. Okay, so that's how that one works. So again, a little bit of wording I'll have to fix up before next time. All right, 4.00 times 10 to the power 3 newtons. So this is the Fg. Okay, I like to make a note of that when I read it. That way I don't confuse it with a mass. Remember, mass is in kilograms. It has a maximum upward acceleration of 2 times the acceleration of gravity and a maximum downward acceleration of 0.25 times the acceleration of gravity. Calculate the tension in the cable for its maximum upward and downward accelerations. Okay. So we're going to start with maximum upward. I'm going to call that part A. So in this one, we're going to have a large Ft, smaller Fg. Okay, so F net is equal to Ft minus Fg. Okay. So if I'm looking for the tension, hold on, let me grab the eraser. I was looking for a therefore symbol instead. Therefore, the force of tension is equal to F net plus Fg. Okay. So Ma plus Mg. Now, when I look at this, I realize that I don't actually have my mass. Okay, remember that to turn a weight into a mass, you need to divide by 9.81. So 4,000 divided by 9.81 gives me a mass of 407.74 kilograms. So 407.74 kilograms onto 9.81 meters per second squared. And then if it has a maximum upwards acceleration of 2 times the acceleration of gravity, I need to take the acceleration of gravity and multiply by 2. So plus 19.62 meters per second squared. So my force of tension is equal to so I get 11,999.78 newtons. And looking at, again, these aren't measurements, so they don't count towards the significant digits. So the only thing I would have is this Fg number and the constant, the gravitational constant. So 3 significant digits, and that gives me 1.20 times 10 to the power of 4 newtons. You'll notice mine are highlighted because the answer key was wrong before, and I had highlighted it to remember myself to fix it, or to remind myself to fix it. In B, if it's accelerating downwards, we have a greater force of gravity than we have force of tension. So F net equals Fg minus Ft. Okay. Therefore, force of tension equals Fg minus F net. So that's Mg minus Ma. And that will give me 407.74 kilograms onto 9.81 meters per second squared. Subtract. If it's 0.25 times, I'm going to go 0.25 times 9.81. So 2.4525. And just give me a second here. I've lost a decimal somewhere. Subtract that number. 7.74. And that gives me a force of tension of 2,999.94 newtons. So 3.00 times 10 to the power of 3 newtons. Okay? And they're both, so calculate the tension in the cable. The tension in the cable for both of them would be upwards. So this one should also say up. Not sure why it says down. Okay. All right. So I think that's everything that I wanted to mention there. Okay. Now you can kind of play around with these and see if maybe these could somehow link you to here from the weight. Again, you might be able to kind of find some shortcuts, but I'm going to leave that at that for now. All right, in a movie stunt, a 95-kilogram actor is dropped down from an invisible to viewer's cable from a height of 32 meters. At the same time, a car, it's 415 meters away. It's driving horizontally. So it'll be perfectly underneath the actor as they get to the ground. So this is a stunt where the person is going to fall into the car, in a sense. Let's think about a convertible. That way they don't crash onto the roof of it. But if you've ever watched Fast and the Furious, you know absolutely anything is possible in those movies. Cars traveling at a constant speed of 80 kilometers per hour. What tension must be in the cable so the car and the actor meet perfectly? Okay, lots of stuff going on here. Let's try and draw a picture first here and see if we can get this all sorted out. So I have my actor kind of dangling from a cable here. Okay, and he's going to be lowered down. Okay, and we have our car. Okay, and our car is heading in this direction at 80 kilometers per hour. Okay, and they're 415 meters away. So from where they are to where the actor is going to be 415 meters. Okay, so if we think about these two, how they relate to each other, and we've done a few questions like this along the way, but the relationship between these two is the time. Okay, whatever time it takes for the car to get to this spot has to be the same as the time that it takes the actor to get there. Okay, so let's kind of see what we can figure out. We don't really have a whole lot about the actor. We know that they're 95 kilograms and they need to drop 32 meters. Okay, we know that there needs to be some sort of tension in this cable. So we're going to start down on the horizontal of the vehicle and we're going to see if we can figure out the time from that. So I know that the car is traveling at a constant speed, so that's nice. I can use my V equals D over T formula. Okay, if I'm looking for time, then time is equal to distance divided by speed. Now the distance is 415 meters and the speed is 80 kilometers. Okay, so that doesn't match. So remember, we can divide by 3.6. So when I do that, I get 22.2 repeating meters per second. Okay, so 415 meters going 22.2 every second. This is going to take me 18.675 seconds. Okay, so when I look at my actor, I know that the distance I have to fall is negative 32 meters. Again, I'm looking like there might be some kinematics to this, so I'm going to include that negative. The actor at the beginning is going to be at rest. Okay. The time that they have is 18.675 seconds. And if you think about, if I'm looking for a force of tension, okay, then I'm going to have a free body diagram. We're going to start over here. So there's going to be an FG, and there's going to be some sort of tension. Now, I know the tension is going to be less than the gravity, or else this person wouldn't accelerate downwards. Okay, so FT is going to be less than FG, so my F net statement is going to look like this. Okay, so for me to figure out the force of tension, I need to be able to calculate FG, which is just mass times gravity. Right now I could do that, 95 times 9.81. And I need to be able to calculate my F net, and that's the mass times the acceleration. I don't have the acceleration of this person, so that's what I'm going to set out to find right now. So D, VIT, and A. So you have a formula that says D equals VIT plus 1/2 AT squared. If VI equals 0, that disappears. So D equals 1/2 AT squared. We're trying to solve for A, so if I divide by 1/2, I get 2D, and then I divide by T squared. And that's equal to A. Okay, so I'm going to punch some numbers in here. So 2 times the distance, negative 32 meters, divided by the time, 18.675 seconds. Okay, so negative 64. And that tells me that I need to accelerate downwards at negative 3.427 meters per second squared. Okay, so now I can go over to what I was talking about before and finish this out here. So I'm just going to rewrite it a little bit larger. So it's equal to FG minus FT. So when I move FT to the left-hand side to make it positive, and I move F net to the other side, what I'm going to be left with is FT equals FG minus F net. So we have 95 kilograms, 9.81 meters per second squared. I'm showing you this time what it looks like if you don't do the factoring. And 95 kilograms onto the 3.427 And notice how I dropped the negative again. So I talked about that earlier in the video. When you chose to subtract, you looked after that negative already. Okay, so remember, we're kind of doing all of our accelerations here as like absolute values. You can think of them. So let's see what we get. So okay, and I got 606 newtons. So now this leads us to two things. One is me having to go back through this and see if this is correct, or see if maybe the answer is potentially wrong. So I'm going to see if I can just quickly sift through this, see if I can find something that I did wrong. If not, I'll kind of let you know in class where we're at and fix the answer up. Okay, the other thing that I could do is I could test this answer out and work my way backwards and see if it worked for me. But so just going to double check some calculations here. So we have 80 kilometers an hour. If I divide that by 3.6, that does in fact give me 22.2. They have 415 meters to go. So 415 divided by 22.2 does give me this time. Okay. Next would be to look at my kinematics formula that I use. So I use D equals VIT plus 1/2 AT squared. You know what I think I might have forgot to do is to square the time. Let me see if that's it. So negative 64 divided by 18.675 squared equals, yes, there it is. Okay, that's my mistake. So again, you can see when you write your work down, you can actually kind of patch your answer together after. Now, in my head, I thought that acceleration was like a little bit too fast. I probably should have checked it at that point, because negative 3.427 would mean that after 1 second, it was going negative 3. After 2, it would be going negative 6.8. After 3 seconds, it would be going negative 9. Like that, just, it would be at the bottom already after like 3 or 4 seconds at that rate. So that should have been my first clue. But either way, I go back, I fix this number, negative 0.1835 meters per second squared, and I want it actually to be positive. Remember, no negatives. So times 95 gives me 914.5 newtons. So a force of tension equal to 915 newtons. There we go. Mistakes happen. You write your work down. It doesn't mean you start over. It means you just make quick fixes. So perfect example of that. All right. Number 4, a man has a mass 82 kilograms while standing on an elevator accelerating upwards at 1.3 meters per second squared. What is his true and apparent weight? True weight is irrelevant to any movement, so it's just equal to mg. So that's going to be 82 kilograms, 9.81 meters per second squared. So 82 times 9.81 gives me 804.42 newtons, 2 significant digits, 8.0 times 10 to the power of 2 newtons. That's the true weight. Okay, now if I'm accelerating upwards, okay, again, accelerating upwards means heavier. Okay, so my apparent weight's going to be equal to my true weight plus the F net. Okay, because I need to be heavier, so I need to add something. Okay, so my true weight, I just figured out, was 804.42 newtons plus 82 kilograms onto 1.3 meters per second squared. And I get 911.02 newtons. So round that off to 2 significant digits, 9.1 times 10 to the power of 2 newtons. All right, number 5, the same man from question 4. I'm going to zoom that so we can see it. Takes the elevator back down with an acceleration of negative 1.3 meters per second squared. What's the apparent weight? Well, I can just use this calculation here, except this time I need to subtract, because remember, when you're accelerating downwards, you're going to be lighter. So you take the true weight and you subtract the F net. Okay, so just using my numbers from before, 804.42 newtons, subtract 82 kilograms. Subtract 82 times 1.3 gives me 697.82 newtons. So 7.0 times 10 to the power of 2 newtons. All right, question 6. So this is our last one here. So a person has a mass of 102 kilograms. We're riding an elevator. They have an apparent weight of 725 newtons. Is the elevator accelerating upwards, downwards, or not at all? What's the acceleration of the elevator? Okay, so person has a mass of 102. So the first thing we're going to do is just figure out their true weight. So 102 kilograms, 9.81 meters per second squared. And that gives me bang on 1,000.62 newtons. So their apparent weight is 725 newtons, which is lighter. So this means they're accelerating downwards. Okay, they have to be going downwards. So what's the acceleration of the elevator? Okay, well, weight apparent, okay, is equal to Fg subtract Fnet. Okay, so they're on the way down, so I know that it's going to be Fg subtract Fnet. Okay, so we have mass times gravity, subtract mass times acceleration. Okay, remember that this number here is just this, so I can plug that in if I want, or I can just start from scratch again. Okay, but I just realized that I'm supposed to be looking for the acceleration, so this is all kind of a bit of a bust. Let me go back to the beginning here. Okay, so if I'm looking for my acceleration, that's contained within this, so I want to get this over to the other side so it becomes positive. So I could add it to the other side, and then I want to get rid of this. So Fnet is equal to Fg minus the weight apparent. Okay, so Fg is going to be that true weight. Okay, so let me just go MA equals and divide by the mass. All right, so Fg is that true weight, so 1,000.62 newtons, weight apparent given to me in the question, and all divided by the mass of 102 kilograms. 0.62 minus 725 divided by 102 gives me 2.702 meters per second squared. So 2.70 meters per second squared, and it's in the downward direction we decided because the person is lighter. Okay, so depending if you've been watching this whole video or not, you would have seen a couple of instances where I got places and things didn't check out. So it even happens to me lots when I'm going through things. That's why I like to make sure I have my work written down. I can go back, I can check things quickly, I can find my mistakes. We're in this situation where I start writing things down. Sometimes I'm like, wait a minute, this just isn't going to help me find what I need to find. I need to go back and read the question again. Okay, so it helps to read questions twice. Take your time, set things up. Other than that, if you have any questions, let me know, and good luck.